Welcome to this explainer. Today, we're getting right into the complex physics behind aerodynamics. We're going to demystify those incredible, invisible forces that dictate the design and, honestly, the blistering speed of modern race cars. It's a fascinating intersection of complex fluid dynamics, brilliant engineering, and raw on-track performance.
So let's just jump right in with a wild thought experiment. If you had a perfectly smooth tunnel, could a modern race car actually drive upside down on the ceiling? I mean, ignoring the fact that all the driver's blood would immediately rush to their head. From a purely physics standpoint, it is entirely possible.
And the answer to how that works comes down to a pretty mind-blowing multiplier, 3x. Modern aerodynamic design is so advanced, it can generate downforce equal to 3 times the actual weight of the car itself. At racing speeds, the air is literally crushing the vehicle into the tarmac with a force 3 times greater than gravity. Absolutely insane, right?
Okay, here's our roadmap for today. We're going to cover the quest for downforce, the physics of ground effect, how we test invisible aerodynamic forces, diffusers and edge vortices, the turbulent air problem, and finally, what active aero looks like for 2026.
All right, Section 1, the quest for downforce and why it actually matters.
So why are engineers absolutely obsessed with this? Well, think about taking a tight highway off-ramp in your own car. To corner faster, you need massive friction between your tires and the road. But if you simply make a race car heavier to get that friction, you're adding mass, which completely ruins your acceleration. Downforce is essentially the magic cheat code here. It pushes the tires into the track for immense grip, all without adding a single ounce of actual mass to the vehicle.
Which brings us to Section 2, the physics of ground effect and how engineers manipulate airflow.
Enter the concept of ground effect. A race car is essentially a giant low-flying inverted wing. By manipulating the tiny gap between the car's floor and the track, and we are talking about a gap sometimes measuring just millimeters, engineers create a massive low-pressure zone. This fast-moving air acts like a giant vacuum, literally sucking the chassis downward. It's the absolute most efficient way to generate downforce, mainly because it creates significantly less drag than those giant upper wings.
Moving to Section 3, testing invisible aerodynamic forces, making the invisible visible. But here's the catch. How do you study this highly complex physics when you literally can't see the air? You might think a standard wind tunnel would do the trick, but traditional fixed floors create unnatural friction that totally ruins the simulation. Instead, researchers have to use highly complex setups featuring a treadmill-like moving belt. This belt travels at the exact speed of the car to correctly simulate the ground moving underneath it, complete with suction slots to manage the boundary layer.
In reality, it requires a massive, incredibly sophisticated laboratory setup. In this environment, engineers can precisely measure how even a single millimeter change in ride height influences aerodynamic grip. This ensures the physics actually hold up when the car hits the track at 200 miles per hour.
All right, Section 4, diffusers, edge vortices, and pumping down the pressure. Check out how beautifully downforce is distributed across a modern ground effect design. You've got 25% generated at the front and 25% at the rear wing, but a whopping 50% is generated entirely by the floor, so the underbody of the car is doing the absolute heaviest lifting to keep the whole thing glued to the track. And that massive 50% from the floor, it heavily relies on a component called the diffuser. Essentially, it's an upswept channel at the rear of the car's underbody. Because the pressure at the base of the car stays relatively constant, this upsweep expands the airflow exiting the floor. By expanding that air, it accelerates the flow underneath the car, effectively pumping down the pressure and creating that immense suction effect we just talked about.
Now this is really cool. We can actually see these invisible forces at work inside the diffuser here. Those swirling shapes are force-enhancing edge vortices. They're basically highly concentrated spinning tornadoes of air that form right off the edges of the diffuser plates. They are absolutely crucial for dramatically increasing downforce, but they're also incredibly delicate. If the car gets even slightly too low to the ground, these vortices can break down, causing a sudden and really severe loss of aerodynamic grip.
Which takes us to Section 5, the turbulent air problem and the threat of dirty air. So, all of this perfectly sculpted airflow introduces a massive environmental challenge when cars actually try to race closely together. This is the infamous dirty air problem. A leading car produces this chaotic, turbulent wake of air behind it. Pre-2022 designs relied super heavily on complex upper body wings, and when they hit that dirty air, they lost up to 46% of their downforce. It made following incredibly hard and caused severe understeer. But by shifting reliance to the floor's ground effect, modern regulations miraculously slash that loss down to just 10%. The floor is just way less sensitive to that turbulent wake.
And finally, Section 6, Active Aero in 2026 and balancing all these forces. So how does all this science build into the car of the future? Well, to balance top speed and cornering stability with the new hybrid engines coming in, the 2026 cars are going to have a significantly smaller footprint. The wheelbase is shrinking from 3,600 millimeters down to 3,400. Plus, the floor will be partially flat to intentionally limit that powerful ground effect, and we're going to see brand new 3-segment active rear wings replacing the older static designs.
By simplifying these key aerodynamic elements and introducing active wings that automatically adjust on the fly, engineers are expecting a massive 50% drop in aerodynamic drag. That's huge. But this efficiency comes at a steep cost. A 30% decrease in total downforce. For us watching, this means a fundamental shift in the sport. The cars are going to fly down the straights faster than ever, but they'll struggle much harder to stick to the track in the corners.
This constant tug-of-war between the regulators and the designer's relentless desire for speed is exactly what pushes the frontier of science. As the new rules strip away 30% of the car's downforce, it leaves us with one really thrilling question to end on. With active wings and less ground effect, what ingenious, invisible aerodynamic tricks are engineers going to invent next to reclaim that lost grip? Thanks for joining me on this explainer, and keep your eyes on the air.